a set of images, all of the same thing, but each one is a little bit different, or maybe a lot different. And what we want to do is take all these images and put them together and get the best possible information out of it. Some examples are medical imaging, like MRI, CAT scans, military satellite images. Say you take ones at different bands in the light spectrum, and you want to combine them to get more information out of them. All these involve image fusion. One good example is the parallel MRI. These are 8 MRI images taken of the chest. I know that these 2 images look black, but there's stuff there, I promise. And so this is the heart, this is the front of the patient's chest. You can sort of see the liver down here and the lung up there. I'm going to trip over that stand eventually. But one thing that we use this image fusion for is to combine these images. So what is a digital image? If you're not familiar with it, it's just a 2-dimensional matrix of numbers where each number at that point represents the intensity of the pixel. Whether it's a black and white image or if it's an RGB image, it can represent the intensity for red, green, and blue spectrum. So what we work with is the image degradation model. We have our degraded image Y, which is equal to our clean image F multiplied by some degradation operator U, and then we have additive Gaussian noise that could be in it, might not be pretty severe, might not be. And so mathematically you might think, okay, well this is all we have to do to solve for this. Why are we really here? But the problem is that this degradation operator oftentimes is close to, if not non-singular, so it's not really invertible, and also your W is not really affected by the degradation operator. So subtracting that from Y, it sort of just screws up the image, and you're not really working with anything that can be inverted versus this. So these are some examples of a degraded image. On your far left you have Lena, that's her name, she's one of the famous pictures in image processing. This is masked. Lena, 50% of the pixels are just blacked out. We're missing all that information. And this is additive Gaussian noise with a variation of 25, but no masking. So what we work with are image patches. Instead of working with the image as a whole, we take 8x8 patches from the image, and we move, and instead of moving over 8 rows and down 8 columns, we move over 1 column at a time and then 1 row at a time. So a 512 by 512 image has somewhere in the neighborhood of 262,000 image patches, which, as I'm sure you can imagine, makes things very hard to work with. Makes them very computationally intensive. But for computational purposes, we take these patches and then vectorize them, and we still can use our degradation operation to represent each patch. Now, why do we use image patches as opposed to the whole image, especially since there's so many of them? These guys up at Minnesota, U. Shapiro and Malott, showed that these patches can be clustered into a finite number of multivariate Gaussians, which have a probability density function shown here. It's basically the same as a normal Gaussian, but with any number of variables that you want. And we use these image patches in their Gaussian mixture model algorithm, which is an adaptation of the MAP-EM algorithm. So assume that we have an initialization for all of our Gaussians, all of our big K number of Gaussians, and we have a mean and a covariance for each one. We can go through, and in the E step, we can take each patch and then, we can take each patch and determine which cluster it belongs in, which Gaussian it fits best in. And then once we've done that for all the patches in the image, we go through the M step, which is where we reevaluate the mean and the covariance for each one of our Gaussian clusters. And then we loop through that. The usual is 3 iterations, and then we're done. Too much coffee this morning. So our E step is it's calculating the maximum log a posteriori probability of our clean patch f sub I given our degraded patch y sub I and whatever covariance of the cluster there is. So we're trying to maximize this, and we can expand it out using Bayes' theorem in statistics or probability, and then using the properties of a Gaussian distribution, we can get this expression on the bottom, which the reason why it's now a minimization equation is if you're taking the log of an exponential that you can see down here, this exponential is negative, so the negative of a maximization is just a minimization. And at first, the first part of the E step is to find in each one of our big K clusters which patch in that cluster is closest to it. So we're able to differentiate over these first two terms to get a closed form solution for each different cluster and find that patch. And then once we have that, we can loop through again for each one of our big K clusters and substitute it in this expression, and then find which one of those is the minimum, and then we have which cluster belongs. So our M step, once we've done the E step for all, say 262,000 patches, we go through, and it's much simpler. To find the mean, you just sum up all the patches and then divide by the number of patches in the cluster. All right. And then the covariance is just the difference between the mean and each patch summed up again over the number of patches in the cluster. And so we loop through that usually 3 times. Now the tricky part is the initialization. And the way that Superior-Malott found was the best way to do this was to use synthetic edge images. And they found, through trial and error, they found empirically that 18 was the best number of edge images to use, because that takes you from 0 degrees all the way to 170 degrees at 10-degree intervals. So obviously that will represent an edge in an image quite well, no matter what angle it's at. And you take 64 patches out of each one of these to use your 64 for your 64 variable Gaussian, 8 by 8 patches, 64. And then you use the eigenvalues of these PCA bases in order to initialize the covariance in each Gaussian, because the mean is always 0 when you start off. Now, that was everything they did in Minnesota. Now, what we're doing is we're adapting this for multiple images. That's where the image fusion comes into play. And so we're now maximizing this log a posteriori for our clean patch given multiple degraded patches and multiple degradation operators. And so the expression turns out to be very much the same, with the addition of the summing over the inverse of the square of the noise level, plus using the number of images as sort of a weighting factor. And again, solving for our clean patches F can be done using a linear filter, which is the same way that we did it before. It's just, again, with summations for each one of our different degradation operators and different noise levels. So some results that we've gotten so far. So this is Barbara, the other one's Lena, this is Barbara. We have names for them because we stare at them all day. This is our degraded image. 80% of the pixels are masked, so they're just gone. Now, using the original GMM algorithm, we get this image out, which is obviously much better than anything we had before. You can actually see the real image, but it's still kind of bad. The texture's off a little bit. It's not very good. But using our fusion model, we have a much better image. Not only numerically, the signal-to-noise ratio is much better, but it's smoother. The texture is much better. It's much more pronounced. It's not as sort of jarring in the single image. But why don't we just take three of these masked images, average them out, and then run the algorithm, because as I'm sure you can accurately guess, it's a lot easier to run it on one image than 3 images and fusing them together. So this is an example of that experiment. So we have 3 80% masked images, averaged out, you get one image that's about 51% masked. And these are the results that you get if you zoom in close on Barbara's face. Numerically, they're not very different. The signal-to-noise ratio of our fusion model is only a little bit better. And to be honest, for the amount of time that the fusion model takes versus running it on one image, it wouldn't be worth it if it wasn't for the eye test. And I don't really know how well you can see on the projector. On my computer, it looks a lot better. But in the single image, it's more staircased in the smoothness, in what should be smooth in her face. There's less detail in her eyes versus the fusion model that we have. Unfortunately, it's kind of subjective, but myself and my advisor and everybody else we work with at least usually likes the fusion model. It can also be used for denoising. Obviously, using the original algorithm running through 4 iterations, we get a clean image out of Lena when she had a sigma of 15 noise. But the difference between the old one and our new fusion model is that if you use 2 of these images, you only have to run it through 2 iterations, which takes significantly less time, and it gets a much better signal-noise ratio out, whereas before we had 30.6, this time we have 31.6, and it takes about 300 less seconds, which is a pretty big jump. Now, the multiple degradations, which is where we really want to go with this, because more often than not, your images are actually going to have more than one problem. They're not just going to be masked, and they're not just going to be noisy. It's going to be a combination of everything. And maybe your signal is going to change a little bit every time, so each one's not going to be the same. So these are 3 different degraded images of Lena, each one different masked, each one different noise level. And using our algorithm, we get this image out. I'm very proud of it. I think Lena looks beautiful. Like I said, we stare at them all day. So this is a cleaned image with a signal-noise ratio of 30.1, where when you consider that each one of these had 10 or lower signal-noise ratio, getting this out is pretty fantastic. We're really excited about it. So if you remember that parallel MRI image I showed at the very beginning, this is what we get out with our model for right now. This is actually an image that has had histogram equalization done on it, and then run through our noise fusion model. And unfortunately, I'll be honest with you, it's not actually nearly as good as the one they have already, but that's part of the point, is we're trying to make it better. We also want to include other degradation operators, especially blurring or in-painting, and then again use these different operators and continue using the fusion model. So these are the references. That's the paper that I kept talking about. Dr. Levine for her love, support, kicking me in the ass. Josh, because he did a lot of the grunt work before I even got on the project. Dr. Kern, who's our stats guy. Katie, who is on the project now, and the National Science Foundation, because they paint. Thank you.